सुनहि बहु विधि सब संता। राम रतन धन जो कोई पाए, जीवन भर रामायण गाए। मंगल भवन अमंगल हारी, द्रवहु सुदशरथ अजर बिहारी। राम सिया राम जय जय राम। 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 जय हो शंकरा, आदिदेव शंकरा। तेरे जाप के बिना चले ये सांस किस तरह। मेरा कर्म तू ही जाने, क्या बुरा है क्या भला। तेरे रास्ते पे मैं तो आंख मूंद के चला। तेरे नाम की जोत ने सारा हर लिया तमस मेरा।
नमो नमो जी शंकरा, भोलेनाथ शंकरा। जय त्रिलोकनाथ शंभु हे शिवाय शंकरा। नमो नमो जी शंकरा, भोलेनाथ शंकरा। रुद्रदेव हे महेश्वरा।
जन्म से भी पहले तेरा वास था। ये जग रहे या ना रहे, रहेगी तेरी आस्था। क्या समय क्या प्रलय, दोनों में तेरी महानता। महानता महानता सीपियों की ओट में जिस तरह मेरे मन में शंकरा तू बसा है उस तरह। मुझे भरम था जो है मेरा था कभी नहीं मेरा। अर्थ क्या निरर्थ क्या जो भी है सभी तेरा। तेरे सामने झुका मेरे सर पे हाथ रख तेरा।
नमो नमो जी शंकरा, भोलेनाथ शंकरा। जय त्रिलोकनाथ शंभु हे शिवाय शंकरा। नमो नमो जी शंकरा,
चंद्रमा ललाट पे, भस्म है भुजाओं में, वस्त्र बाघ छाल का है खड़ा पाँव में। प्यास क्या हो तुझे, गंगा है तेरी जटाओं में, जटाओं में, जटाओं में। दूसरों के वास्ते तू सदैव ही जिया, मांगा कुछ कभी नहीं, तूने सिर्फ है दिया। समुद्र मंथन का था समय जो आ पड़ा, द्वंद्व दोनों लोक में विषामृत पे था छिड़ा। अमृत सभी मैं बांट के, प्याला विष का तूने खुद पिया।
नमो नमो जी शंकरा, भोलेनाथ शंकरा, जय त्रिलोकनाथ शंभो हे शिवाय शंकरा। नमो नमो जी शंकरा, भोलेनाथ शंकरा, रुद्रदेव हे महेश्वरा। नमो नमो जी शंकरा, भोलेनाथ शंकरा, जय त्रिलोकनाथ शंभो हे शिवाय शंकरा। नमो जी शंकरा, भोलेनाथ शंकरा, रुद्रदेव हे महेश्वरा, रुद्रदेव हे महेश्वरा, रुद्रदेव हे महेश्वरा। नमो नमो जी शंकरा, भोलेनाथ शंकरा, जय त्रिलोकनाथ शंभो हे शिवाय शंकरा।
मधुरं मधुरं वलितं मधुरं चलितं मधुरं भ्रमितं मधुरं मधुराधिपतेरखिलं मधुरं वेणुर्मधुरं रेणुर्मधुरः पाणिर्मधुरः पादो मधुरं नृत्यं मधुरं सख्यं मधुरं मधुराधिपतेरखिलं मधुरम्। गीतं मधुरं पीतं मधुरं भुक्तं मधुरं सुप्तं मधुरं रूपं मधुरं तिलकं मधुरं मधुराधिपतेरखिलं मधुरं करणं मधुरं तरणं मधुरं हरणं मधुरं रमणं मधुरं वमितं मधुरं शमितं मधुरं मधुराधिपते।
Hello, mic check. 1, 2, 3. Hello. check. Hello. Mic check. Hello. 1, 2, 3. Hello. 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 Check. Hello. 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 Mic check. Hello. Hello.
करणं मधुरं तरणं मधुरं हरणं मधुरं रमणं मधुरं वमितं मधुरं शमितं मधुरं मधुराधिपतेरखिलं मधुरं गुञ्जा मधुरा माला मधुरा यमुना मधुरा वीची मधुरा सलिलं मधुरं कमलं मधुरं मधुराधिपतेरखिलं मधुरम्
हेलो 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 हेलो
गोपी
हेलो हेलो
मधुरा लीला मधुरा
हेलो
युगं मधुरं
हेलो हेलो
मोहं मधुरं दृष्टं मधुरं श्रेष्ठं मधुरं मधुराधिपतेरखिलं मधुरं गोपा मधुरा गावो मधुरा यष्टिर्मधुरा श्रेष्ठिर्मधुरा दलितं मधुरं फलितं मधुरं मधुराधिपतेरखिलं मधुरम् अधरं मधुरं वदनं मधुरं नयनं मधुरं हसितं मधुरम् अधरं मधुरं वदनं मधुरं नयनं मधुरं हसितं मधुरं हृदयं मधुरं गमनं मधुरं मधुराधिपतेरखिलं मधुरं वचनं मधुरं चरितं मधुरं वसनं मधुरं वलितं मधुरं चलितं मधुरं भ्रमितं मधुरं मधुराधिपतेरखिलं मधुरम्
हेलो हेलो
वेणुर्मधुरं
हेलो माइक टेस्ट
रेणुर्मधुरः पाणिर्मधुरः पादो मधुरो नृत्यं मधुरं सख्यं मधुरं मधुराधिपतेरखिलं मधुरम् गीतं मधुरं पीतं मधुरं भुक्तं मधुरं सुप्तं मधुरं रूपं मधुरं
ज्ञान मंजरी इनोवेट
बैल जैसे धूल उड़ा के
सिर्फ पढ़ना नहीं और सीखना है, स्किल को अब जीतना है।
रट्टा अभ्यास छोड़ो, कौशल लक्ष्य शिक्षा से जोड़ो, प्रोफेशनल लर्निंग मेथड अब हर स्टूडेंट बनेगा एक्सपर्ट।
ज्वाइन ज्ञान मंजरी इनोवेटिव यूनिवर्सिटी भावनगर।
तो हेलो हेलो
हेलो
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 हेलो हेलो Everyone, please settle down and take your respective seats. We're about to start soon. Everyone, please settle down and take your respective seats. We're about to start soon. Everyone, please settle down and take your respective seats. We're about to start soon. Everyone, please settle down and take your respective seats. We're about to start soon. Good morning, everyone. Come on, it's first international conference of Gyan Manjari. Good morning, everyone. Good morning, distinguished guests, respected dignitaries, and dear participants. Myself, Vaibhavi Bhatia, with my co-host, Krisha Jogi, and it is our absolute honor to welcome you all to Gyan Manjari International Conference on Research and Innovation. Today is day 2 of GMICon, where each and every theme speaks about science, pharmacy, and sustainability.
Yesterday, we witnessed an inspiring beginning of this conference with insightful discussions on the themes of engineering, IoT, and artificial intelligence, and green technology. The sessions highlighted how rapid technological advancements are transforming our world, creating smarter systems, and paving the way towards greener and more efficient solutions for the future. Building upon the strong foundation, today, we move forward into another quality, important, and impactful domain, science, pharmacy, and sustainability.
These themes remind us that scientific innovation is not just about discovery, but also about creating solutions that improve human health and preserve our environment. From advancements in pharmaceutical sciences to sustainable scientific practices, today's discussion will focus on how innovation can contribute to a healthier, safer, and more sustainable future for society.
We would like to extend warm welcome to our esteemed guests, dignitaries, by presenting them with bouquets as a token of our respect and gratitude. I would like to invite Dr. Nimbak sir to present the bouquet to Dr. J.R. Chunawala sir. Next, I would like to invite Dr. Ishita Raninga ma'am to present the bouquet to Dr. H.M. Nimbak sir. May I request everyone to give a warm round of applause. We now invite Anish sir to deliver the opening address. It is my distinct privilege to introduce our esteemed Director of Training and Placement at Gyan Manjari Innovative University, Professor Anish Vora, who will deliver the welcome address for GMICon to 2026. Sir, we request you to kindly share your thoughts.
Thank you, Kaya. A very good morning to all. Our today's distinguished chief guest and keynote speaker, Dr. J.R. Chunawala, Provost and CEO of Gyan University, Dr. H.M. Nimbark, convener of our international conference, Dr. Ishita Raninga, respected faculties of Gyan University, all the innovators, researchers, delegates, and students. I am very much honored and privileged to offer a very warm welcome to you all on the second day of this Gyan Manjari International Conference on Innovation and Research. This is second day our innovators and researchers will publish their research work in post-lunch session. Yesterday also we had different tracks from engineering and technology, and I am very much proud to announce that more than 70 research papers were presented in offline as well as online mode. And today the same scenario, and today also we have poster presentation in post-lunch session also. So our theme is innovation for sustainability and sustainable future. So why? Why we always talk about sustainability, or why the need has arisen that all the innovators and researchers should start their work for the sustainability. We all know that there are a lot of challenges at a global level. We have climate change, we have depletion of our natural resources, we have loss of our biodiversity. So what actually we say development, but we should ask ourselves that is it a sustainable development? That is why the theme is innovation for sustainable future. We have to work on the research work, all the innovation that should be for the sustainable future. So today, all the researchers are ready, and I am sure that whatever work, innovations they will present, that will be to ensure for the green and safe world tomorrow. So with this, I again offer my welcome to you all in the second day of this first international conference of Gyan Manjari University. I welcome you all. Thank you. Thank you very much.
Thank you, sir, for those inspiring and motivation words. Your address has truly set the meaningful direction for today's proceedings.
With this auspicious beginning, we now move forward into the core of today's conference. Science continues to redefine possibilities, pharmacy strengthens global healthcare systems, and sustainability ensures that our progress remains responsible and future-ready.
To further enlighten us, we are privileged to invite a visionary leader. Since becoming Provost and CEO of GMIU in July 2023, he has elevated Gyan Manjari from excellence to preeminence through his BE, MTech, and PhD in Artificial Intelligence from Nirma University. This isn't administration, it's transformation at scale. Previously Executive Director and Principal at Gyan Manjari Institute of Technology since 2015, an Associate Professor had at B.H. Gardi College, Dr. Nimbark masterfully coordinates innovation cells while fostering interdisciplinary research that bridges academia, industry, and global challenges. Under his leadership, GMIU doesn't produce graduates, it creates nation builders, ethically innovative professionals ready for AI-driven sustainable futures. Through ethically innovative professionals, the man who turned vision into institutional reality now inspires our collective future. Let us welcome with thunderous applause Chief Patron Dr. H.M. Nimbak to deliver the keynote address.
Thank you, Vida. Again, on this second day of conference, international conference of Gyan Manjari Innovative University, this is first conference, and this is the second day of that first conference. Again, as yesterday I talked something about the research, few things I already elaborate on that day. Again, this similar task has been assigned to me on this occasion. With very warm heart, I welcoming on behalf of the Gyan Manjari University, I am welcoming Chunawala sir, the dignitaries on the dais, off the dais, directors, COE, cluster directors, head of the departments, event coordinators, research coordinators, my dear students, and all researchers. Yesterday, as I something elaborate about the research in general, I mean, I'm not here to just talk about my domain, because this is the second day, and on second day we are focusing on chemistry, I mean science, as well as the pharmacy. Both the area that we are going to cover. Researchers has researched on this area. Some researchers has prepared the poster on this area. As yesterday, something elaborate about the research. Two type of institutes are there, as I already discussed, research institute and academic institute. Research institutes are already producing the research and transforming to the industry in terms of technology transfers, as CSMCRI what actually doing. Educational institute again producing the research which can lead the students, which can allow the students to critically think, and the students can definitely contribute to the research field. This is what the basic area or motivation behind these kind of conferences. Not only that, some of the industries are really keen to do research work, but they couldn't able to do, and where these kind of institute are morely beneficial to that kind of industries. What I mean to say, research can be, right now the research area which is required in general, if we'll talk about energy, which we are facing lot of problem because of the war. Again, the urban density is increasing day by day, which is required the involvement of the researchers, how to sustain in the urban density. Again, the environment, again the big issue. We have to live in the environment, we have to, sustain in the environment. So what can be done through? But the more important thing that I would like to elaborate today, highlight today, is that what are the role of the educational institute in terms of research activity. See, right now, if anybody, after completing the 12th science, if anybody would like to further study in a chemistry area, for example, because in 11th, 12th, we have studied physics, chemistry, maths, biology. If we like to study in chemistry, I'm very much interested in chemistry, for example, then I have to think about that what are the different options are available. If we'll talk about our institute, we do have pharmacy, we do have industrial chemistry, we do have BSc in chemistry, just chemistry, we do have biochemistry, we do have forensic science, we do have fingerprints. See, are you getting my point? Why research is important? Because when you are selecting particular field, you your whole life you are spending behind that, and with that also, you would like to grow your career also. It is not just that you would like to study only. You don't want to grow, you don't want to develop your career. It is not like that. We definitely would interested in research, but at the same time, we would like to develop our career in research itself. So these are the options. When these are the number of options, these kind of options are available, we have to be very much conscious, and we have to be, when we are selecting any of the areas, still, if you are in chemistry, you can consider it a minor honor as a particular subject, and you can work it out. Even in a fourth year, again, as I said, that you can spend whole year in a research field. Now, if we talk about the overall field of the pharmacy or science, there are a lot of changes are going on. Lot of changes, if we'll talk about. In terms of what? Let me tell you, in 2023, see, basic drug, that is paracetamol, for example, I'm talking about, that paracetamol, overall, the molecules scarcity has been increased because the US is, producing more dominant into that, and the cost increased by 7%, or not only that, but the profit margin of the our company is been reduced to 10% only. In that case, some of the good company like Dr. Reddy, Biocon, Zydus, these kind of company thought about that what can be done. So what they did is, they convert from volume to value through research. I'm pinpointing this, why research is important. Volume to value. What they did is, they spend maximum of the revenue, divert their revenue towards the research in terms of biosimilar drugs. What they did is, they produced the inhaler, they produced the relief spray, and the result of that, let me give you some of the figure. The result of that, the biosimilar market by 2026 and end of the 2025, it is increased to 10 times biosimilar market. What I'm talking about is $1 pill can be produced $5,000 similar biosimilar pills. They focus from volume to value. And because of that thing, what happened right now, in a world, the India has been considered as a oxygen of the pharmacy of the world. India has been considered as a pharmacy of the world. This is just not because of the, we are having these or that. No, it is because of the research in different area we identify some of the area which are untouched. There was a gap. And because of that thing, in a similar field, lot of other fields are also there. I'm just giving the example of pharmacy area. But similar, so many other areas where these kind of things been happening. And because of that thing, the industry has been sustaining, or not only just sustaining, but growing like anything. Let me give you some more figures. Like because of the product link incentive from the government, 1,100 crores revenue is being generated in the early of 2026. Because of the research, the synthesis of a biocatalyst reduce waste by 15 to 20%. The waste is been reduced because of since this is the figures of the last 2-3 years I'm talking about. In India, the clinical trial, the rules is being changed. The rules now focusing on human biology based models, not on animals. And because of that thing, the translational gap is been reduced in significant manner. and the failure of the drugs is been also reduced up to the 92%. Try to understand. Up to the 92%, it could be reduced and been reduced. Also, because of all these things, the multidisciplinary, interdisciplinary approach, that chip is not been made by the pharmacy or science students, but chip is made by the engineering students. The model, human model, is been made by the AI-driven and other, the field of the engineering. But because of that thing, the drug discovery cycle is been reduced from 12 years to 5 to 7 years. See, आपको भी पता है और मुझे भी पता है कि हमें कोरोना की वैक्सीन कितनी जल्दी मिल गई थी, and how corona vaccine we exported to the different countries, and how it could be possible because of these research areas. So I would like to, don't want to go much deeper into that, but would like to say that Indian pharma companies are spending their overall the revenue, 7 to 9% of their own overall revenue they are spending in the research field. And because of that, nowadays, yesterday I told you, the patent has been increased since last 3 years. The patents 20 to 25, between last 5 years, registered patent or patent draft is been increased to 88% in India. We are the third largest after US and China for patent producing. In that area, pharmacy and science contribution is 25%. And this is because of the research only. So what I mean to highlight today in general, that what is the importance of the research in particular these areas. These are some of the areas that I would like to cover right now within 5-10 minutes. But if you will drug deep into this, you will find that there are a lot of other areas that you can contribute. You can develop your career in this area, and you can sustain in the world, as our name of the conference is Sustainability with Innovation. So again, I wish कि आपके सभी रिसर्चर्स, सभी रिसर्च जो है वो कहीं ना कहीं आपके करियर में आपको यूटिलाइज हो या सोसाइटी को बेनिफिशियल हो. आप ट्राई करें कि आप मोर एंड मोर फोकस रह के जो भी रिसर्चर है वो इस पर्टिकुलर एरिया में, अपने खुद के एरिया में ज़्यादा से ज़्यादा रिसर्च करे, ताकि सोसाइटी को उसका बेनिफिट मिले, इंडस्ट्री को उसका बेनिफिट मिले. थैंक यू अगेन, थैंक यू ऑल.
Thank you, sir, for your insightful words. Your vision truly inspires innovation and excellence. Now, sir has some urgent meeting, so he has to attend. And thank you, sir, for your presence. It is now time to hear from distinguished personality in the field of science.
It is a great privilege to introduce our next keynote speaker, Dr. J.R. Chunawala, an eminent chemical engineer, distinguished scientist, and an inspiring leader in the field of chemical process development and engineering. Dr. Chunawala completed his BE in chemical engineering from the prestigious National Institute of Technology, Rourkela, and earned his PhD in chemical engineering from Sardar Vallabhbhai National Institute of Technology. With an illustrious career spanning more than 33 years, he has been serving at CSIR, Central Salt and Marine Chemical Research Institute, Bhavnagar, since December 1993. Currently, he is a chief scientist and leads the process design and engineering group, where he has played a pivotal role in advancing chemical engineering research from laboratory innovation to industrial commercialization. Dr. Chunawala's expertise lies in chemical process development, scale-up engineering, separation technologies, inorganic waste utilization, magnesium-based specialty chemicals, and micronutrient fortification of salt. Over the years, he has successfully contributed to the development of numerous innovative chemical processes, including production of precipitated calcium carbonate from carbide lime waste, recovery of industrial salts from waste streams, hydrotalcite synthesis, zeolite A production from low-grade bauxite, potash recovery from bittern, and development of nutrient-fortified salts, among many others. His remarkable scientific contributions have resulted in more than 30 international patents and 20 Indian patents, with many of these technologies successfully transferred and licensed to industries. His outstanding work has significantly strengthened the bridge between research, innovation, and industrial application, giving him exceptional expertise in technology, scale-up, and commercialization. Among his notable recognition, Dr. Chunawala received the CSIR Technology Award 2013 for developing a process for manufacturing synthetic hydrotalcite from pigment industry effluents, a technology that led to the establishment of a 1,000 TPA capacity plant. Earlier, he was also honored with the CSIR Technology Award in 2001 for the production and commercialization of K. carrageenan from Euchema seaweeds in India. More recently, his contribution to double fortified salt technology was recognized among the top 100 Indian innovations in 2022. Dr. Chunawala is also an active member of esteemed professional bodies, including the American Institute of Chemical Engineers and the Indian Institute of Chemical Engineers, where he holds life membership. With his extraordinary contributions to chemical engineering research, sustainable process development, and industrial innovation, Dr. Chunawala continues to inspire researchers and industry professionals alike. Ladies and gentlemen, please join me in giving a warm welcome to our esteemed keynote speaker, Dr. J.R. Chunawala.
Hello. I'm audible? Okay. It's my pleasure to be here with you, Professor Vora, Professor Nimmark, and dear students. In this occasion, I would like to talk about ways to well technologies for sustainable solution, circular economy we have developed at our institute. This is our parent organization, Council of Scientific and Industrial Research. Prime Minister is our president, Minister of Science and Technology is our vice president, and Dr. N. Kanaisamy is our director general. And we have 37 laboratories all over India, similar to CSMCRI Bhavnagar. And about CSMCRI Bhavnagar, our institute is established in 1954. Our basic aim was to develop salt quality and salt yield improvement, because in 1947 also we used to import salt. Then after 60s, we expanded our activities in the field of marine chemicals and seaweed. This is our present building. And this is our Mandapam Mars near Rameswaram. They are working on this seaweed cultivation, edible and non-edible. These are, we work around seawater. Our main area are salt, solar salt, marine biology, and halophytes, membrane, and marine chemicals. These all our working area at CSIR, CSMCRI Bhavnagar. These are instruments. We have top class world-based equipments at our institutes. So at our institutes, we select a process route where waste should not be generated at first place. The process has to be integrated and maximum yield and minimum waste generation. Utilize all the waste generated and find out the niche application or reducing waste in the process. Some of the key well-to-wealth research at CSMCRI, value addition of nitrophosphate plant GNFC Barut, sodium silicate, precipitate silica from kimberlite waste, diamond mining waste, precipitate calcium carbonate from carbide waste, hydrotelsite from effluent waste, sodium sulfate from textile and tannery waste, potash fertilizer using C-biton and other waste, magnesium chemicals from seawater. This is good technology, must yield asymmetrical gains and present-day constraints must be protected by IPR and eco-friendly. We undertake all research at the Institute at clear sense of purpose and focus on sustainable technology, development and licensing. This enables us to create maximum impact on society in the shortest possible time frame. So some of our recent achievements: first commercial plant, 60 KLD per day at Aurangabad to recovery of potash from molasses. First commercial plant using low-grade bauxite at Naredi, Kutch. Development of sodium sulfate, sodium recovery at Chinakarai, Tamil Nadu. Potassium carbonate recovery for Vinati Organic, Mumbai. Synthetic hydrotelsite for human multinational, Germany. This is simple salt process. Just seawater is pumped to reservoir, then it is after some calcium sulfate and calcium carbonate is separated, then bittern is generated. This is simple process of salt manufacturing. So this is also some flow diagram of how salt is produced. This is cycle of just 45 to 60 days salt is produced. So just in our Purana, Samudra Manthan is mentioned. So sea is a source of valuable chemicals. So we are working on salt and marine chemicals also. Suppose 1 lakh ton salt is produced, so equal quality of mother liquor is generated. And this mother liquor is valuable source of magnesium and potassium chemicals. So this is the one-top phase equilibrium diagram developed by Wantoff during 1918. Very good base, one of the base paper for seawater separation. So our seawater sulfate is present, and that be Israel's C-biton sulfate is not present. So God has gifted to Israel. We have very difficult to separate potassium chemicals from C-biton, but we have overcome this sulfate problem, and we have developed novel process for potassium. Why potassium is important? In India, we are not a 1 gram of potash we are producing in India. Totally 4,000 crore we are importing from Russia and Canada. Because now in geopolitics, our potash price is double. So these are the local solution for fertilizer. Similar to phosphate also. Total phosphate we are importing. So this is how potash is produced. Bittern is a mother liquor from salt industry. If sulfate present, then kyanite type of mixed salt is produced. Sulfate is not there, carnallite is produced. So in Israel bittern, carnallite is there. In Indian bittern, sulfate is there, so we have to process kyanite. So these all are sonite, syngenite and carnallite. These all are scheduled fertilizer. So this is also how evaporation 29 Bohme means 1.25 gram per cc. So how this N-bittern is generated and mixed salt is generated for potash production. So this now Nirma is located here. They are producing, I think, soda ash and 2,000 ton per day. So they generate calcium chloride as a waste, 10 to 15% of calcium chloride. So we develop novel processing using this calcium chloride, and using calcium chloride we have desulfated, and desulfated bitumen is converted to carnallite. So we have overcome the sulfate impurities, and we have made equivalent to Israel bitumen. So in this carnallite, it is very easy to separate KCl and MgCl2. So this process also we have transferred to Hindustan Lever. So low sodium salt nowadays means for hyper BP, low sodium salt is used. But Tata and other Nirma, they are also producing low salt, but they are physically mixed. 15-20% KCl and 70 to 80% is sodium chloride. So in situ, low sodium salt can be generated. So this process also we have developed and transferred to Hindustan Lever and ITC. So this is again low sodium salt. Low sodium salt means we have in Gujarat 2.25 wasteland is 2.5 lakhs million hectares are wasteland. So this in arid land this can be grown. So we develop using siliconia into this low sodium salt. We developed process this 2017 when Prime Minister came to our exhibition. So this is a photo of this low sodium salt. And sulfate of potash. We initiated potash research during 1960s, and slowly we expanded other activities, and this process, integrated process, means zero waste. All streams we have utilized. Mixed salt, in mixed salt, ammonium sulfate is again fertilizer, and magnesia is also for refractory application, and for magnesium metal for space applications. So this is also in LRK. LRK is lower run of Kutch. So in Kutch also, brine is available, similar quality of Israel. So we have identified 25 ton muriate of potash can be generated. So we are working on PDIL, and they are going to set up one pilot plant there. This is again magnesium chemicals. Byproduct bitumen magnesium content is 4%. So 4% is very good amount, and we develop all this magnesium chemical range of all the means India's, I think 70 to 80% magnesium chemicals are produced in Bhavnagar. This is the new novel magnesium hydroxide for refractory. We have steel plants, so all magnesium refractories we are importing. So we develop this process for refractory applications, and we are working with our sister laboratory, CGCRI, Kolkata. And we have signed MOU with 2 or 3 big magnesium manufacturers for steel applications. And our sister laboratory is also working on magnesium metal. Magnesium metal is very light material. It is used in space crafts, space applications. This is spent management for molasses. So nowadays we are these ministers, they are telling about this alcohol blending. But alcohol blending, if we means very difficult, because 1 ton of alcohol generates 10 ton of spent waste. So spent waste is a burning issue for production of alcohol. So we develop novel processing using distillery to potash process. So this is because of this spent water dumping in Ganga, and their water is contaminated in Uttar Pradesh. So this is again, using spent washes. Some manufacturers, they burn this spent wash in an incinerator. So incinerated ash also contains almost 10 to 15% of potassium sulfate. So we successfully developed and Seram, they have installed plant 4,500 DPA, and they are also first time in India they have started production. Effluent utilization for synthetic hydrotalcite and potassic salt. Synthetic hydrotalcite, it is novel feature chemical. It is used in pharmacy also for carrier of molecules. India, except Huber, nobody is manufacturing. It is layered type of material, just like sandwich. In magnesium, aluminum hydroxycarbonate, we can remove carbonate and we can exchange whatever stable compounds. So application is polypropylene production. During polypropylene production, residual chloride exchange with this hydrotalcite and plastic life extends. So we developed this process in Huber company. Huber is a Ferrari-red company, 400-year-old German company. So we work with them, and their waste is ammonium carbonate and aluminum chloride. Both raw materials are used for this production of synthetic hydrotalcite. And there are many applications. We all we have in our house syntax tanks. So in ppm or micro ppm level, we are consuming lead, because lead stearate is cheaper than hydrotalcites. So in India, no rules. Germany and USA, they have banned these stearate chemicals. In future, definitely this has future markets in India also. So he is M.M. Sharma. M.M. Sharma is one of the chemical engineer from University, and we received one award also for this application. Many Reliance are major user of this chemical. This is again stream of potassium carbonate and sodium carbonate. Vinati Organic, they are producing isobutyl benzene. Isobutyl benzene is used in ibuprofen. Ibuprofen and world's 80% isobutyl production produced by Vinati Organic. So they have problem of waste, potassium carbonate and sodium carbonate. One R.D. Paik, American scientist, he has spent 30 years for separation, and they are importing potassium carbonate from France. But we have also worked on this. After many trial errors, we have successfully separated K2SO4 and Na2SO4 at room temperature. And they have installed process. A plant is running at their Vinati Raigat Maharashtra plant. This geolite and silica from kimberlite waste. Geolites is a cation exchanger, and hydrotalcite is a anion exchanger. Geolite, it is used for in a detergent. In detergent in India, phosphate compound is used. So phosphate is banned because phosphate is responsible for eutrophication. And in Germany, in all European countries, it is banned. But we are using phosphate, and totally phosphate we are importing. So means this is novel compound for phosphate industry also. So kimberlite is a waste generated during mining industry. Every 10 carat of diamond, 100 ton of kimberlite is generated, and kimberlite is a valuable source of magnesia and silicates. 20% is magnesia and almost 30% of sodium silicate. So we utilize these diamond mates. We work with National Mineral Development Corporation, and we develop this geolite process using this kimberlite. And first, our plant established at Odisha, National Aluminium, using that pregnant liquor of alumina plant. Second plant is Naredi with low grade bauxite. and both plants have 10,000 TPA capacity. These are, we are totally importing previously. Now we have sufficient capacity of Zeolite 4A for detergent applications. And another is now Madhu Silica is located in Bhavnagar. They use the silica for silica production. They use sodium silicate as a raw material. So, sodium silicate produced from sand and caustic soda. But we developed novel process using this fly ash and rice husks. So this is called green tire, green silicate, green sodium precipitate silica for tire applications. Reject salt management in tannery and textile sector. So textile sector, our GDP 4% and almost 4 to 10% textile and tannery sector. So all plants are located in, mostly located in southern India. So if they, initially they face with their waste problem, and they have partially they have closed units, and means 30 to 40 lakhs are people are working and mostly women. So partially closure of these units are also lot of social problems. So they have adopted the zero discharge process. After zero discharge process also they have waste generation, huge amount of waste generation. So with our knowledge, simple solubility equilibrium process, we have separated both sodium silicate and sodium sulfate. And at Chinakarai plant, they have successfully, they have invested almost 10 to 15 crore for our process, and plant is running. So this is effluent at Chinakarai plant. This is our pilot scale demonstration. In right side is their commercial plant. This is also a very simple process using phase equilibria. These are some this press media. Okay, this is again precipitate calcium carbonate. Precipitate calcium carbonate is produced using limestone, but in calcium carbide, carbide production, hydroxide is generated. These millions tons of calcium carbonate, calcium hydroxide is at Kota site. So we have successfully produced first time veterite type. Veterite type calcium carbonate is used in paper application. So we develop and transfer this technology to DCM Sriram, Kota. This is again value addition of waste generating nitrophosphate plants at GNFC. In fertilizer nitrophosphate plant, phosphate rock is reacted with nitric acid and for calcium nitrate, and calcium nitrate again reacted with ammonium carbonate for ammonium phosphate fertilizer. So every day, per day, they generate 100 ton of byproduct calcium carbonate. So we successfully developed and transferred this technology. This is bench scale 10 kg for our continuous, semi-continuous plant, and we develop paint and rubber grade of calcium carbonate. And this is seaweed addition. In 90s, Pepsi, one of means employee of Pepsi, Mr. Abhiram Sheikh, he came to us for some seaweed means consultancy. And that time for seaweed derived protein used for pet food. So that time we means work for this, and we successfully Eucoma seaweed and this other seaweed we have successfully cultivated in Indian means seawater, and then we transferred this technology to PepsiCo. And then Abhiram said led company, and they have started Oat Agri company. And now our director, he is working on this biostimulant. And now Sagarika, our Pepsi, this Abhiram Sheikh, total 100 crore company takeover by IFCO. And biostimulant is substitute for the chemical fertilizer. So we have studied almost 43 university, almost all the vegetables, all the crops in India. And these are our just photos of our industry clients. This is also again MM Sarma. This is our 3 TBD plant at our site in Bhavnagar. This is Archean Chemical. Archean Chemical is also in Kutch. So we have demonstrated potash to them. So these are some news related with effluent. These are all our collaborators, clients. Thank you. If anybody having any questions related with technology or our institute.
If anyone wants to ask any questions.
Means we work on waste, we work on biofertilizer. Biofertilizer is also, biostimulator is also alternative of chemical fertilizers. So our work is related with sustainable. We work for sustainable future and zero waste process we work. And we are also working on lithium and uranium from seawater. These are our future research.
Thank you, sir, for enlightening insights and valuable contribution. I would like to invite Professor Amit Maru, sir, to present memento to Dr. J.R. Chunawala, sir.
Now, we move to our global segment of the conference.
We are delighted to welcome Dr. Mohit Mehta, Marie Curie Fellow from Tampere University, Finland, for the online plenary session. Dr. Mohit Mehta is Marie Curie Fellow at Tampere University, Finland, with over 6 years of postdoctoral experience across India, South Korea, and Finland in biomaterials, microfluidics, and nucleic acid delivery. He has secured over 1 million euros in competitive research funding across his appointments in South Korea and Finland. In 2024, he was one of the 3 young scientists selected to represent Finland at the 74th Lindo Nobel Laureate meeting in chemistry and the only EU nominee from Finland.
Thank you, Chunawala sir, for such an insightful session. I'm hoping that everybody is really enlightened with the research that is going on at CSMCRI, Salt and Marine Research Institute. Sir, the session was very much insightful, and we got to know very much about the current trends and the current research that is going on at the CSMCRI, how the salt is being occupied, how the bittern is being processed, how the magnesium, potassium, everything is being processed and reused, how sustainability is also an important category in your institute, how it will be useful in the future itself, not only in other countries but India too. So it was an insightful session, and I'm hoping that everybody present here, all the participants, all the students, all the faculty members were highly insightful with this lecture. So with that, I'm highly thankful to J.R. Chunawala sir, and we will like him, if he wants to leave, he can proceed with that. Thank you, sir. participants to please be seated because we still have an online lecture. So we'd like Dr. Mohit Mehta to continue with his lecture. Thank you very much, sir.
Hi everyone. I hope I'm audible. Yeah. So let me. Yeah. So today I'll be speaking a bit about organ on chips and how we at the Tampere University are using. Sorry. Yeah. And how at the Tampere University we are using this technology to basically create a human organ environment in the chip. Before I begin the organ on chip, let me tell you what is the problem and why we are doing it. As we know that usually any drugs or medicines that requires to treat any illness requires a lot of time and money to invent. So usually the invention and prototyping, it takes almost 3 to 6 years. Then we move to the preclinical phase where we test these medications on first 2D cell cultures, mice, rabbits, and monkeys, and all the animals. And once it passes that phase, we'll move to the clinical phase in which we test them on humans. Now, the problem is this is the highest failure rate phase, the clinical phase. The reason being said, when we are spending over 15 years, over 2 billion euros, and still very few medications makes to the end where it can be used to treat the actual disease it intended for. And what is that? And why is that? So over 90% drugs fail in human clinical trials. So after over 10 years of work, when we are doing amount of money on the research, still over 90% of drug fail in a human trial because, first of all, when we are testing them on a 2D cell culture, it's a static culture. It doesn't represent the human. And when we test them on mice, we cannot, it doesn't translate with the human thing. Simply being said that over 90% of drug when fails, that human biology is different than actual mice or rat biology. But still we are doing it. So why? The very first thing is that we always know that mice and humans shares 90% of the genetic background. That being said, we have over 90% same DNA. Of course, historically, it does make sense when we are sharing 90% of DNA with some animal. Why not test the medications on them? However, the true hard fact is identical genes does not mean identical biology. So the divergence, which is a 10%, that actually does make day and night of difference. And that is the reason why over 90% of drugs that passes preclinical animal trials usually fails in human trials. Now, why? So usually we think that just we scales the body down and every human biology or anatomy scales down as well. But nothing can further from the fact. Usually when the organism's size decreases, the metabolic rate increases much faster. With being said, smaller bodies requires a very high amount of metabolism, which in turn converts to a heat to stay alive. So basically, any drug, if we eat the drug, it may take few hours in our body to digest. Mice can digest in over few minutes. So that is the very first problem. The second problem is the cardiovascular problem. Usually by visual look, the human heart and mice heart is the only visual difference is their size. However, in the biology, if you compare the normal cardiogram of a human and a mice, you can see the QT interval. The interval between the one heartbeat is vastly different. So mice heart beats around 600 beats per minute compared to us, which is 60. So if we have over 600 beats per minute, we probably would have died within a few minutes. So we cannot compare the drugs cardiotoxicity. Even if we are treating the cardiovascular, if we are treating the cardiovascular diseases and we are making the drugs for them, we cannot test effectively on mice because they may be caused arrhythmia in human, but may not on the mice. And we think, oh, okay, it's fine, and I'll just eat it. But then the human trials, it fails. The same goes with the lungs. We breathe around 12 to 20 breaths per minute compared to mice, 200 to 300, which means that they absorb oxygen and air around 10 times higher than us, maybe more than that. Also, our lungs are designed to have a cyclic physical strain. So basically, when we inhale and we exhale, there is a strain that comes to our lung, which forces our alveoli to work. Now, if we are doing 10 times or 20 times more strain on this lung for the rest of our lives, this lung will collapse within a few days because they are not made to breathe that long. And that is the fact. Plus, we have a very high complex branching. So basically, there are so many other complex materials and the pathways built inside our lung, which mouse doesn't have. So we purify air in a much better way compared to mice. And this diffusion and all these phenomena will take consideration when converting into the final drug output. Now, when we ingest any drug, the main organ which converts the drugs into its biotransformations is the cytochrome P450 enzymes. And usually these enzymes are responsible for degrading or transforming any material into our body. So basically it breaks down it into smaller parts, which are easy for us to digest. Now, mice possesses around 100 of these enzymes, and we have almost 57, so almost half of what mice have. With that said, mice, so in a simpler term, mice has over 100 spoons to eat the same amount of food versus we have 50. That translates to a very big problem. For example, in past, the vancomycin acid, which once was an anti-inflammatory drug, that passed the animal trials with flying colors. We thought, okay, it's fine. But when it's been given to human participants, it caused severe jaundice and liver injuries. So it just produced different metabolites in human than compared to mice. So again, if it is safe for human, it can't be safe for a human. It's not that guaranteed about mice and human. Now, the kidney, because ultimately we want the drug to clear our body. We want it to get out from our body once it does its job. And that comes to a part of the kidney. Now, kidney is our filtration system. It basically filter out all the waste materials and try to provide us with cleaner blood. Now, in this whole filtration system, the mice is filtering it at a much higher rate compared to human, Basically, we have a kind of a conservation system that even if we are filtering, so kidney tries to conserve as much as water back to our body and only throw out the toxins. That's not the case for mice, and which in turns provide us the more time in our body for drug to be there. For example, a well-known example is the cadmium. Usually cadmium, if we ingest the cadmium, our endothelial cell layers disrupts. However, because mice has a very faster filtration rate, it just rapidly clear its pathway, and there is no cadmium in mice after few hours compared to us, which is around few days or weeks. So cadmium gets more time to disrupt us compared to mice. Now, the one of another problem is the microbiome. When we think about food poisoning or something which we ingest and create a metabolite byproducts, that is waste. That is a EHCA, for example, E. coli or anything metabolites that aggravates the inflammation. Now, historically proven, we only shares 4% of the microbiomes with mice. And the reason is mice usually breeds in a clean facility with little to no exposure to toxins, bacteria, virus, germs, nothing. Compared to we are living in a quite brutal environment when we are exposed to all the toxins, virus, bacteria, and whatnot. So our body is usually designed to have a more microbiome compared to the mice, which just doesn't have it. So it's just change how we absorb the medicine, and we cannot say that okay, it's good for mice. And sometimes the vice versa is also possible, that it is safe for human, but it's not safe for mice. So sometimes we just lose a good drug that it kills the mice, but probably was nice to us. So now, because these are so many problems, when we cannot compare mice to human, then what is the solution? Because we need to get our drugs tested. So the answer to that question is organ on chip. And what we are developing is we are developing a tiny bit of chip that replicate human body microenvironment and also the mechanical microenvironment. So on the right hand side, you can see an actual developed chip which has the all inlets and outlets, which I'll explain just in a bit. But basically it has the live human tissue of any particular organ. And because of this all flows and chemicals, it behaves as a human, live human organ. So now we can test something on a human organ, which is supposed to be ingested by human organ. So there is no chance to fail. Now, this means a microphysiological systems or an organ on chip, which usually use primary human cells or iPSCs. iPSC means that induced pluripotent stem cells, which has the potency to become any organ cells they desire. So basically we can scale down the fluid dynamics, shear stress, and mechanical strength, basically every living aspect of human body into a chip. So how do this chip works? So this is the chip that I have shown just now. It is connected with cell reservoirs, some pneumatic pumps, as well as the excretion collecting system. Sounds familiar, right? I mean, this is basically how human works. We eat something, we breathe here, and then we throw the waste out. So same thing, cells, and these are the cells or the human or the organ that which we would like to replicate. Now, one thing, let me make very clear. This is the whole chip's aim is to replicate the microenvironment of a tissue. It does not grow whole organ to transplant into human. So that is far from the reality. The only thing that these chips are designed to do is to replicate human organ microenvironment to test the drugs or effect of any kind of toxins, materials whatsoever. So we can inject the material or the fluid, which is the media in the case of chip, which translate to human blood using the inlets. We provide air to the cells with the pneumatic pumps, which basically replicates the breathing. And then these are the outlets from which we flush out the waste, basically how we live. So why we need to do this and why can't we do it in a old petri plate? The reason is our cells are a living system. When we put them out of this all the strains, fluid dynamics, shear stress, they basically forget what they are built for. For example, if they are heart cells usually forget to just blink, or they don't beat after a while because they forget that they are heart cells and they need to blink. So same goes with the lung. They forgot to they just can't breathe anymore. So that's why we need to provide them a constant environment for which they are designed to. So let's first show me the heart on chip. When I say heart on chip, it might look like, you understand, it might look like this, but it does not. It looks like this, which looks boring, but it is the heart, how heart tissue function. So if I show you the diagram, so this is the inlet from which we insert the fluids, also known as blood, and from outlet it just washes out all the fixation that is created by the cells. So this is the actual picture of the heart on chip, where the heart tissues are there, and this is inlet, same outlet, and here the heart tissue is beating. Let me show you an example. So this is the how heart on chip, basically this is the real image of an heart on chip using a SEM, and you can see the heart, how heart is behaving. So heart is just breathing normally. We can see that actually that heart is breathing normally under normal conditions. But the moment we introduce a drug, for example, norepinephrine, we can visually see that it is beating much faster rate now. So this kind of thing you cannot ever do with the mice. So this is the small pillars, which also known as cantilevers, and these are the heart muscles in the diagram. You can see compare. So basically this and this pillars, microarrays, basically sense how this heart is beating. Is it beating faster? If faster, at what rate? Basically, we can only see from the eyes, we cannot quantify. The role of these pillars is to quantify how this heart is beating at faster rate and what. So when we can introduce so many things to this chip now and study the actual human heart. For example, we can simulate a heart attack. I mean, I don't see a reason where we can do that on a human. So this is as close as we can get to the replicating human, that we can basically deprive the chip of oxygen, which is also known as hypoxia, which induce the tachycardia and then followed by arrhythmia. And you can actually measure all this phenomenon from that one little tiny chip, that how this whole phenomenon is taking place. And that is the biggest advantage of having a teeny tiny organ on a chip. Now, the lung on chip. When we are breathing, our air is basically, there is a microscopic layer of a various small lines or a globule, which basically absorbs the air and transfer it to a blood the way it understands. So when we are making a lung on chip, what we can do is construct a flexible, transparent, biocompatible polymer-based chip, which features this kind of microscopic channels. The whole channel can be featured within with the living human cell, and it can continuous breathe. However, it does not create the whole lung. Again, let me make it very clear. But it just do construct the alveolar capillary, like how the teeny tiny one of these small veins which actually breathes. Let me show you what I mean by that. So this is the typical lung on chip and how it looks like. It is made of this type of vacuum chambers separated by a polymeric membrane. And this is a membrane with lots and lots of gaps within. So on the top of that, you deposit the lung cells. On the bottom, you are using the normal capillary cells to support the system. And when you provide vacuum, basically the whole chip breathes like an actual human breath. Now, when you pass the air from the upper side, this air actually get absorbed and passed down using this transmembrane and to the blood. Now, let's say if there is an airborne virus or a bacteria. So this basically same with our human lung. It deposits to these lung cells, but in blood we have white blood cells. So basically they just travel, eat the bacteria alive, same way they are doing within the human body. And you can actually see that these are traveling there. So all these white lines, these are real images of the white blood cells which are stained and they are taking over the infection. I don't see any other way to do this or replicate this into the mice or visually see that on actual human cells. So what we can do with it? Let's say we have seen the SARS-CoV-2 and there was no way to give someone COVID and check how they are behaving with it. When you can give that to mice, but once again, as I said before, it just doesn't make any sense to do it anymore. So basically, we can stain the molecule, stain our cells, and somehow when it comes to the contact with COVID, these lung on chips can detect it very easily. It can tell us that how our human immune system is behaving with it, and we can simply get direct high resolution time based reading all day every day. So it allowed us to see and basically emulate the lung microenvironment with a real-time visualization capacity. Same, this kind of chip has been used to measure the toxicity as well. So in this chip, we can dye our cells. So based on the toxicity or the environmental toxicity, for example, if we stain them with some kind of a biomarker, in a simple term, this biomarker just make it fluorescent enough to visualize from our own eyes or a microscope in this case. So basically, it just, if it is dead, then it turns to red. If it is alive, then it still stays blue. And with this kind of biomarkers, we can measure the effect of radiation, some smaller particulates, or any foreign materials, how they behave in our live lung. And the very last organ, the liver. Now the problem with liver is liver metabolize a lot of things. So it just doesn't made of with the same one type of cells, but it requires several type of cells. The first one and the majority one is the hepatocytes, which are the liver cells, and they are the factories. They have handle metabolism, how they handle urea synthesis, albumin production, and everything. So these are the main part. Over 80% of liver is made of hepatocytes compared to endothelial cells. Now, basically, we require some kind of a protection. So endothelial cells are kind of a protection which provides a vascular walls. It basically to transport the nutrient. The third one, buffer cells. The whole reason for them to exist is to fight the infection once occurred. So basically, these livers, endothelial cells, usually tries to stop it at the border. Somehow, if it invades, the buffer cell will take care of it. And last, the stem cells. It does every type of regeneration in the liver. Why I explained all this? Because to understand how liver actually works, we need to check that liver is not just a simple mass of organ. It is constructed from millions of this type of polygonal and hexagonal structures, and it is known as hepatic lobules. Now, blood travels from outside to inside. This is our central vein. And when it just travels, it filters out and it throws out the excretas. And this one little tiny globule do all this work. Now multiply it by a million. So that's why you cannot just compare it with mice again, but we can make this type of a small globule, and people have already made it. So these are the small one globule which filters the all the things which it need intended to filter, because there are actual liver cells. All the four cells that I've mentioned before is inside each of these things, and they are basically filtering through a microscopic network of channels, and then it goes to the axis to the center. So this is basically your excretion vein. Now, by all doing this, and why we are doing this, so what is the ultimate goal of this? The ultimate goal is to create a body on chip where we can connect all these different organs in parallel to create a whole human. Imagine that you can create a whole human and conduct an experiment on it without even needing to touch a human. So, and for now, it is a now fact that we have replicated almost every organs, miniaturized them, and replicated into the microfluidic platform. So now these are, and some of them are actually, you can buy it right now. They're already available by many companies, some of them. So next time, if you are going to test your medication or drugs on a mice, think once, and you can test it on the actual human cells or a human. And what is the goal? So the goal is to have a personalized medication trial, because as we know, every human reacts very differently to drugs. So something is safe for me may not be safe for others. Same goes with all kind of drugs, all kind of toxins, all kind of materials. So now with this, we can actually test the drug on very own cells before we actually needing to take the drugs. So even the drugs are safe for everybody, you can still test it on yourself without actually testing it on yourself. That is the whole game of this whole game of this our research, that we can do with personalized medications. And with that said, we are aiming for more accurate results, more efficient, plus ethicals, because usually one drug can kill thousands and thousands of mice. So ethical part is also very important, and it is a personal. With that said, thank you, and I'll be happy to answer if you have any questions. Yes. Thank you. So yeah, that is a very good question indeed. So first of all, we are not aiming for consciousness at all. Let me be very clear about it, because that is something we are not interested in. There are neurons on chip, for example, which can replicate the human brain, but to basically draw a line where consciousness is a philosophical question, to be honest. But it can replicate a part of an organ for sure. Now, the second part is the ethical aspect. Of course, when you are using the human-based cell lines, there is an ethical problem lies there, or there is some kind of a concern. But when you weigh in the benefits it carries for the whole animal trial thing, because as we know, usually we need to kill about thousands and thousands of mice because before we can even produce a single effective drug. So when and these tissues or the cells usually are being gathered from the organ that are been either donated or basically been removed from the person with of course their approval. So most of the time there is no ethical problem as long as the donor is aware of the fact what they are giving it for and what is the role their tissue is going to serve.
This is the first international conference for the Gnan Manjri Innovative University, and our topic of innovation for a sustainable future has highly been a remarkable conference for both the days, yesterday and today. So with this, I would like to thank first and foremost Dr. H.M. Nimbak, the chief patron of the international conference, our chief guest, that is Dr. J.R. Chuniwala, our other online chief guest, that is Dr. Mohit Mehta. Both the sessions were highly insightful. The research work was highly innovative, and I am hoping that all the students, the faculty members were able to understand how sustainability is helping and shaping the future in research and innovation. So Dr. Mohit Mehta, your research was highly innovative, and I'm hoping that everybody was able to gain really novel insights into how the chip is working and how microbiology and biology can help in sustainability as a bridging or interdisciplinary sustainable innovation topics. So with this, I would also like to thank conveyor, that is Professor Riddhi Malvania, my co-conveyors, Professor Deepak Jhani and Professor Rahul Parmar. I would also like to thank all the faculty members, the directors, uh, the cluster directors, each and every faculty member from all the domains in the Gnan Manjri Institute, the committee members, the student committee, each and everyone, the IT team, the teaching and the non-teaching staff, everybody that has contributed to making this GM Icon 2026 a successful event. So with this, I would like to conclude this thanking session. Once again, thank you everyone. All the participants, thank you again for your contribution to this innovative conference. Thank you everyone.
Thank you, ma'am, for those gracious words. With this, we conclude the inaugural session of the conference. We now invite all the offline delegates and the faculty members to proceed for the lunch.
After the lunch, kindly proceed to your respected allotted venues on time as we will be moving towards our parallel presentation sessions, oral and poster presentation sessions, which include science, pharmacy, and cross-disciplinary themes. The locations are for session 7, it's TF27, for session 6, it's TF25, and for session 8, which is poster presentation, it's in TF19. After the lunch, please stick your posters if you are in poster presentation. Thank you, and all the best. Enjoy your lunch.